So good morning, everyone, or good morning or good day, depending on where you are. I think it's time to start, isn't it? I can see that we have 62 participants already. So, but more will come, I guess. So welcome to ERA's webinar. My name is Per Nilsson. I'm the president of ERA, and this is our, see here, our fourth webinar that we host online. And today's topic is the uncertainties in indoor radon measurements. And our guest speaker will be Dr. Zornitza Daraktchieva. I tried at least. She's the team leader of radon dosimetry in the UK Health Security Agency. We'll get more presentation later on. First, I would like just to mention a bit about ERA. It was founded in 2013, and the purpose of the organization is to serve as a platform for the exchange of information and networking for radon experts, as we do today. We address all radon sectors, companies, research facilities, and authorities. And we are registered under Belgian law as a non-profit international organization. Our goals is to promote public awareness of radon, to provide communication network for all radon professionals and other relevant groups. And here I would like to mention our journal of the European Radon Association, JERA, where we publish radon-related articles, and the webinars, of course, to encourage the development of quality standards. That's more about the topics today. Education and training, and serve as a pool of experts. Finally, I would like to mention the Rooms 2022 in Bergen in September. It's a cooperation between ERA and hosted by the DSA, the Norwegian Radiation and Nuclear Safety Authority. It's strongly recommended. It's a conference in Bergen and excursion to Kinsarvik, the most radon-prone area in Europe. So it's really, it would be a really great meeting, and I really recommend you to register. And we, as organization at ERA, we handle the registrations, and you can find more information about ERA and the memberships. There will be a discount on the conference for ERA members, but you can have a look at our webpage, and you can also register for the event, the Rooms 2022, on our webpage. So please have a look there and register for Rooms. But now for today's webinar, you are invited to ask questions, but only using the Q&A space that you can find in the bottom or in the top of your Zoom client. It's marked with the Q&A. Maria will collect the questions, and if necessary, cluster them and ask the speaker afterwards the questions, and she will answer. And finally, the webinar is being recorded, and it will be available on the ERA website later on. So I think I'll leave the floor to you on the web for you. Sorry, for uncertainties in indoor radon measurements. Please go ahead.
Yeah, if you can stop sharing so I can share.
Yes, of course.
Yes. Quite strange Zoom today. Hopefully it's working. First, hopefully it's a little bit weird. It's not the first time. Okay, this is not the first site. Okay, I'll go. I don't know what's going on, but anyway. Okay, it's a little bit weird today. Could you see my screen?
Yes.
There is still a small screen next to it and I cannot sort it out, but I prefer just go through presentation, and this is just the next slide. No, nothing else. Okay, good morning, everybody, and thank you very much for the opportunity to present before IRA, which is the great community, and I admire it, and I'm a member. Okay, so today the topic is the uncertainties in indoor radon measurements, and I'll try to explain the complexity of the problem, and hopefully at the end I'll try to solve some of the misunderstandings about this, hopefully. The outline of the presentation will be the basic concepts in measurement uncertainty first will be covered. Then temporal and seasonal variability of indoor radon will be discussed. Year-to-year variation of indoor radon, spatial variability, short-term versus long-term measurements to predict the annual average radon concentrations, uncertainty, error, precision, and accuracy in indoor radon measurements, classical and non-classical error, instrument uncertainty for passive edge track detectors. It's just okay, I don't know what's going on. Classical, non-classical errors, instrument uncertainty, and for active instruments, electronic radon integrated detectors.
Sorry, I'm really sorry to interrupt, but
yeah, sure.
We seem to be stuck on slide number 10. That's all we can see on the other side. Can you?
I don't know. Okay, Maria, in this case, could you please, you try to share, and I'll, because I shared with you the PDF version of the
I'm going to
I'll stop share, because it seems that mine is automatically going.
Okay, that's fine.
I'll stop share.
Give us a second, we'll just restart. Pia, are you okay to put up Zora's presentation just because of my
I will try.
Issues? That's great.
Yeah, actually, also we saw only one slide of your presentation. So
yes, I heard it.
So,
sorry for that.
Yeah, okay.
Right, well, let's see. Apologies, everybody. We'll just restart so we can make sure we get Zora's presentation from slide 1. We'll be back in a second.
Yeah. Hey, it's Murphy law. We know it. It's from physics, so it's fine.
Okay, this is strange, isn't it?
It goes to yeah. You can go to.
So can you see anything now?
Or... Yes, we can see, and it moved as you were moving it.
Okay, perfect.
If you go to full screen, hopefully.
Yes.
We have about half.
I think we have some problems with that, but you can see here.
If you go to the right button, yeah, this one, yeah.
Yeah.
Okay, so yeah, I use my glasses because I cannot see, and the other monitor is not sharing, so it's fine. Okay.
Now you can see the outline.
Yes. The outline, yeah.
Yes. Okay. So I guess I have to be your.
Yeah.
tell
Sorry
me
about
to,
this.
Yeah.
Yeah. Next slide, please. Yeah. Okay, let's start with basic concepts in measurement uncertainty, and there are two major documents connected with measurement uncertainty. This is so-called GUM, and which is actually guide to the expression of uncertainty in measurement, and VIM, which is International Vocabulary of Metrology. These two documents define measurement uncertainty in 3 ways. First one, this is a parameter associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurement. The second one, a measure of the possible error in the estimated value of the measurement as provided by the result of a measurement. And the third one, an estimate characterizing the range of values within which the true value of measurement lies. The subject of the measurement is called the measurement. In our case, this is the radon concentration. The result of a measurement is called measurement value, and it is given in unit of sensor. Could you please go to the next? Yeah. The previous one. Okay. Yeah, the next one. Yeah. Okay, the next parameter that we need to define is the error. How GAM defines the error? The measurement error actually has two components, random and systematic errors, and this is important to distinguish between these two. Random error arises from unpredictable or stochastic temporal and spatial variation of influence quantities. Although it is not possible to compensate for the random error of measurement result, it can usually be reduced by increasing the number of observations. Systematic error, on the other hand, cannot be eliminated, but can often be reduced. If a systematic error arises from a recognized effect of an influence quantity on a measurement result, the effect can be quantified and a correction factor can be applied to compensate for the effect. Next one. Okay, let's put this into perspective. On the left-hand side, you see a plot, which is not a real plot, it's just visualization. I cannot use my obvious pointer, but with green, this is the true value. It is a single value, so-called true value. I'll explain in a while. With red, it's a red line, it's given the measured value. And the measurement error is the difference, is defined as the difference between the true value and measured value. But the problem with, for example, real measurements like field measurements and indoor radon measurements is that we don't know the true value. This is directly applicable when we have calibration, for example, because the true value in this case is the reference value. And you see that the measured value is a single line, but what we have is the dispersion of the measured values around this mean measured value. Why is this? Because our instruments are not perfect. They cannot produce a single line of measurement. And because of this, the measurement uncertainty is a measure of the statistical dispersion of values distributed around the measured value, which is the mean. It is a quantification of the doubt about the measured value. For values distributed normally around the mean measured value, MV, which is given here, the uncertainty U is given with standard deviation of the distribution, and this is the classical formula of standard deviation. The result of the measurement is expressed as MV plus minus U, and in this case, it is 68% confidence level, which is 1 sigma or 1 K. If you want to have 95% confidence level, which is 2 K, we have to double the value of U. Okay, thanks. Yeah. The other two important parameters in measurement uncertainty are the precision and accuracy. And again, there is on the left, there is a plot, which is again this visualization, and which try to visualize the accuracy and precision. The accuracy is the proximity of measurement results to the true value. In our case, this is a reference value. Reference value, more or less, could be a very good match to the true value. And it describes both random and systematic errors. Precision, on the other hand, is repeatability or reproducibility of the measurement, and it describes random errors. Precision is given with the width of this distribution. Okay, next slide, please. Yes. Okay, let's start now. Again, return to radon. I'm sure that most of you know about radon, but just to cover the basics. Radon, and especially radon-222, is a noble radioactive gas with half-life of 3.8 days. It has no smell, color, or taste. Radon is a decay product of radium-226, which is a decay product of uranium-238. It can be found everywhere. And you can see the decay chain of radon, which contains alpha beta decay progenies. Next slide. Okay, so why we're concerned about radon? Outdoor, the measurements worldwide provide that in most places outdoor radon is quite low. However, the things are quite different if we build a house. And inside a house, radon is always higher than outdoor radon. Why is this? There are 5 sources of radon that determine the amount of indoor radon in a house. These are the soil beneath dwellings, water supply, gas supply, building materials, and outdoor air. Actually, the main source of radon is the soil beneath dwellings. And why radon gets into a house? Because of a small under pressure, negative under pressure between indoor and outdoor. Indoor, we have a higher temperature than outdoor, and this temperature difference is the drive for soil gas radon to get into the building from beneath. Another factor is the wind. The wind strength and direction also creates under pressure, and again, radon can get into house because of this. Okay, next one. Okay, what affects the radon levels in a house? The exact amount of radon in a house, it is difficult to estimate, but we know that is determined by the following factors. Radium content of the soil, permeability of the ground beneath, entry routes into the house, occupational pattern of the residents, ventilation rates. In addition to the above parameters, the movement of radon is influenced by the following environmental parameters: outdoor temperature, pressure, wind speed and direction, and rainfall. All the above parameters, with the exception of radium content of the soil, very constant. So we can expect as a result that radon will vary. Okay, this is a particular example of how radon is influenced by 2 of the environmental parameters, which are the wind and temperature difference. In this, on this plot, you can see the bottom graph represents radon. The middle one is the wind speed, and the top one is the temperature difference. If you look a little bit more carefully, you can notice that radon and wind speed are negatively correlated, and radon and temperature difference are positively correlated. So, these are real measurements, and the publication is given as the reference. Okay, please, next slide. We understand that radon varies, but it's not as simple. Actually, the radon variability has 2 components, and these are the temporal variability and spatial variability. And this will be discussed now. Okay, this is the example of temporal variability of indoor radon, more specifically daily variations. On the plot are given the measurements, daily measurements of radon. And the difference here is in order of a few thousand difference between the different days, from, for example, below 50 becquerels per cubic meter, which is some of the lowest points, to a few thousand. It is quite significant daily variations. Okay, so next one, please. But apart from the daily variations, we know that there are so-called seasonal variations. I would like to note that different countries have different seasonal variations of radon. And in this plot are shown the specific seasonality or seasonal variation of radon indoor radon in UK. You can see that in the summer, the radon levels are the lowest. And in the winter months, January, December, radon levels are the highest. But as I said, every country has its own specific pattern of seasonality. And another example of temporal variability of indoor radon are so-called year-to-year variations. This is a very good example of radon, year-to-year radon variations. The measurements are done by Daniel Speck in 98 houses in Minnesota for 17 years. Each measurement was a year long. And he found that the typical year-to-year variation was about 25%. The first plot shows no trends for about 88% of the houses, there are no specific trends during these 17 years. But for 7% of the houses, he found that there is increasing temporal trends. And for another 5% of the house, there is decreasing temporal trends. Okay, thank you. The next one. Another variability of radon is the spatial variability, and this is the map of the European indoor radon, which shows the spatial variability of radon in Europe. The map reports the arithmetic mean of annual average indoor radon concentrations in rooms on the ground floor. The red and orange colors represent countries with higher radon concentrations, and with blue, thank you, and with blue and green countries with lower radon concentration. You can see this on the reference and the publication. Next one. Another example of spatial variability of indoor radon is the UK radon potential map, which shows the spatial variability of radon in the UK. This map is a little bit different to the previous one because it displays the radon probability. It is a probability map. The map identifies areas with elevated radon potential, where at least 1% of homes could have radon levels at or above the UK actual level, 200 meters. So the probability is shown with colors. The darker the colors, the bigger the probability that the properties will be in areas with elevated radon potential. The map uses measurements in 2 rooms, and geological data is provided by British Geological Survey. This map is done in collaboration with British Geological Survey. Next slide, please. Another example of spatial variability is manifested of vertical variation of radon inside homes. And in these tables are given radon levels that vary vertically within homes. These are studies from Canada, Finland, UK, and USA. There are various studies, that's why there are several data sets. And the ratio on the right, which is highlighted with red, provides that, for example, living room to basement, bedroom to basement, or upper floor to lower floor ratio is less than 1, which means that radon levels decrease with an increase of the story. Next slide, please. The spatial variability of radon in homes is demonstrated by another study, this time from UK. There are 389,000 homes. On the left are given the radon levels as geometric means in the living room, in basement, ground, and first floor. And you can see that the radon levels decrease with an increase of the story. On the right-hand side are given the bedrooms. For the bedrooms, the decrease is noticed only from the ground floor to the first floor. There are some assumptions why it is the case, but again, still there is a decrease of radon with the increase of the story level. But not only vertical variation of radon is noticed and documented. There is so-called horizontal variation, which means that rooms situated on the same story or floor also could vary. And again, example from UK, where 120,000 homes were studied. It was noted that there is a difference between 2 studied rooms called living rooms and bedrooms. There is a difference of 5% between them. Okay, next slide, please. Okay, what are the implications of radon variability for indoor radon measurement? The first and most significant one is there is not a constant value of radon for any period of measurement. The measured value changes over time. The temporal and spatial variability of radon in a chosen period can be a few orders of magnitude different to the average value measured over other periods. Yes, this is a particular example from a from a local school. If you look at the plot, there are given daily variations of radon. However, if we try to estimate the average radon concentration, which is done very rough calculations on the right-hand side for different measurement periods, 4 days, 7 days, 14 days, and 20 days, we can see that the arithmetic means that are measured through these periods are different. But not only this, the standard deviation is bigger than the arithmetic mean. If we calculate the coefficient of variation, coefficient variation is the standard deviation divided by the mean. It is also called the relative standard deviation. You can see that this is higher than 100%. And this indicates that the data, this particular data, is highly variable. Okay, next. Okay, next question that everybody that starts to do radon measurements is asking themselves. Are short measurements not enough? Could we predict the annual average radon concentration with short-term measurements? And this is an illustration of the difficulty of predicting the long-term measurement and annual average radon concentration from screening results. This is again an example from studies in America by Daniel Steck. And you can see on the y-axis are given the screen results, and on x-axis are given the annual average radon concentration. And the correlation between the short-term screening results and annual average is quite weak. R squared is 0.38. It is difficult to predict the annual average from short-term measurement. Next slide. Okay, let's put the measurement uncertainty in the context of indoor radon measurements. The measurement uncertainty analysis. This is a process of identifying and quantifying possible errors to estimate the total measurement uncertainty in indoor radon measurements. Contribution from sources of variability should be identified and separated from the instrument uncertainty. The uncertainty in indoor radon measurement involves the following errors: random errors due to temporal and spatial variability of radon, systematic errors, classical errors, and non-classical so-called Bergson type errors. I'll explain these errors later on. It is possible to quantify only the sources of laboratory and instrument uncertainties, as these are classical errors. Okay, let's look at the most popular radon detectors, which is passive radon monitors. And in this presentation, I will review the measurement with so-called solid-state nuclear track detectors. They are also called passive edge track detectors. There are three materials that are widely used: PADC, LR115, and macrofol. And they are given here in PADC closed, LR115 open, and macrofol closed configurations. These detectors are used for long-term integrated measurements of indoor radon. They use plastic as detector material. Radon damages the surface of the plastic, and damage is made visible by chemical or electrochemical etching. Okay, sources of error in measurement with passive edge track detectors. The passive detectors are made of plastic material. The plastic material is cut, processed, etched, and analyzed. And each of these processes involves some errors. The quality controls ensure that detectors comply with the allowed uncertainties of each process, but there are uncertainties. The uncertainties of each process should be measured and quantified. This is one of the methods. And the other method is to estimate the total uncertainty that should be measured. Okay, the classical errors, the errors that can be measured and estimated easily. These are laboratory sources of measurement error that can be quantified. Uncertainty in radon calibration reference value, variation of the etch track material, variation in the etching process, uncertainty in the automatic track counting and analysis system, uncertainty in the linearity of response, uncertainty in the chemical change of the plastic, aging, and fading of material. Okay, there are two approaches of how we can estimate the laboratory uncertainties. These are so-called bottom-up and top-down approach. The bottom-up approach identifies all measurement errors contributing to the total laboratory uncertainty and then calculates this combined uncertainty. The top-down approach estimates the total uncertainty by inter-laboratory intercomparison. And just examples. This is an example of the bottom-up approach. This is the publication from the Irish laboratory that underwent the ISO accreditation. The measurement uncertainty is estimated from all known errors contributing to the total error. Right? On the table, on the first column, you can see the sources of uncertainty. Uniformity of radon gas in the chamber, within sheet variability, uncertainty from atmosphere during exposure, calibration of certain patterns, aging effects, fading, repeatability, and all of these uncertainties, actually they're here calculated as the relative uncertainties or coefficients of variation. They are used to calculate the combined standard uncertainty and 68% confidence level K equal 1. This is 13.6% uncertainty. The expanded uncertainty to 95% confidence level in this example is 27.1% on the right hand. Okay, yeah, it's okay. Thank you. Next one. Another way to estimate the laboratory source of measurement error is the top-down approach from inter-laboratory comparison. And this is an example of intercomparison in which the total measurement uncertainty is given as percentage measurement error. The percentage measurement error is consisting of two errors, biased error and so-called precision error. The biased error is the measurement mean and the reference minus the reference value divided by reference value. It's actually estimated the percentage of the accuracy, the accuracy. And the precision error, which is defined as standard deviation over measurement mean, is the coefficient variation. So with these two errors, the percentage measurement error is calculated. On the right-hand side, you can see we correct some examples how detectors are exposed next to each other in the UKHSA radon chamber. I would like just to notice something interesting. In the previous example of the Irish laboratory, you remember that at 1 K or 1 sigma, the uncertainty was given as 13.6%. It's interesting to note that from the intercomparison, the same uncertainty was given at about 11%. And the top-down approach with inter-laboratory intercomparison in most cases is lower, gives the lower uncertainty than the measured through individual laboratory uncertainty. It's interesting just to know. Probably because in some occasions, people overestimated some materials. Okay, next slide, please. Okay, let's see what are the uncertainties on measurements in dwellings, and especially on estimating the annual average radon values. It should be noted that in dwellings, detectors are exposed to the unknown radon concentrations. We don't know the true value. We don't have this. Therefore, the laboratory sources of measurement errors should be considered in combination with the following additional errors. Uncertainty due to temporal variation of indoor radon in dwellings. This uncertainty can be minimized by extending the period of measurement. Uncertainty due to spatial variation of indoor radon in dwellings can be minimized by increasing the numbers of monitoring points. Uncertainty on extrapolating the monthly measurement result to the annual average radon concentrations. This can be minimized by some extent by use of seasonal correction factors, for example. Uncertainty on extrapolating the 1 year result to any other year can be minimized by estimating the annual variation of indoor radon in an area or a country. Next. Okay, here are given some measurement periods and how well they can estimate the annual average radon values. This is done by calculating the coefficient of variation. In this example, coefficient of variation is the period of the result for a period divided by the result of annual average. And the results are from Minnesota, US, UK, Finland, and include different measurement periods. Shortest one is 2 days and longest is semi-annual. You can see from the table that the shorter the period, higher the coefficient of variation is, and vice versa. The longer the period, the smaller coefficient of variation is. Also, in this case. Okay, what are, however, the uncertainties when we do long-term average radon levels? The sources of uncertainty in the long-term average radon concentrations should include the temporal but spatial uncertainty as well. And here is in this table are given sources of uncertainty from, for example, 3 months versus 1 year long measurements of 25%, spatial variation within the house of 30%, variation over years of 30%, and combined uncertainty in this case is 49%. It does not mean that this combined uncertainty should be applied to every country and every single house, but this is just a good, very good example as how this estimation should be done. Okay, next one, please. Okay, let's try to look and see what are so-called non-classical errors. They're also called Bergson type errors. They cannot be easily quantified. They can be modeled to some extent. Example is uncertainty in the measurement due to change in people's behavior in the monitored premises, changes of ventilation rate, holiday period. For example, a measurement is done by a laboratory and they assume that people there occupy the building for the whole period, for the house for the whole period of measurement. However, people decide to go to holiday. In this case, the measurement is not representative of the normal behavior. And uncertainty in this case is a Bergson type. Uncertainty due to spatial variation between radon activity concentration rooms in a house. 1 or 2 rooms are monitored, but results are applied to the whole house. Uncertainty in the measurement protocol. People are advised how to place detectors, how to record the start and end of the monitoring. But it is uncertain to what extent they follow the advice. Okay, and now I will look at active radon instruments that are also used to monitor radon concentrations in dwellings. These active instruments provide time resolved measurements. The air is either pumped or diffused into a volume. Each instrument requires a power supply. They have fast response time, as suitable for short or long-term measurements. And here at the bottom are given the 3 most popular instruments. The AlphaGuard, the first left. In the middle one is the Atmos and RAD7 on the right-hand side. Okay, please next slide. What are uncertainty in measurements with active radon monitors? There are laboratory sources of measurement error, and these sources can be quantified. These are uncertainty on the background. The background can be measured. On the linearity of response, on the radon calibration reference value. These all 3 can be measured. However, the measurements in dwelling produce the other sources of error that cannot be quantified during the measurement period. The uncertainty on cross-contamination with other altimeters, uncertainty on drift of the instrument. Okay, and now lately there are a lot of new radon detectors available that differ from the traditional passive and active radon monitors. These are called electronic radon integrating detectors, or we call them IRID. IRID specification goes that the air is diffused into volume. Some require a power supply. They're suitable for short or long-term measurement. They provide integrated radon measurements, and some of them also provide time-resolved measurements. Some of the most popular are given on the right, like Canary, Raman, Alpha, Corentium Pro, AR Plus, Radon Scout, Wave, and Radon 9. Okay, what are uncertain measurements with IRID detectors? IRID instruments have the same uncertainties as active radon instruments if they are used for time-resolved window radon monitoring over a period of time. However, if they are used for the estimation of annual average radon concentrations, they will have the same uncertainties as passive radon detectors. Okay, and conclusions. Uncertainty in indoor radon measurements is a complex problem. The measurement uncertainty involves systematic errors associated with laboratory sources that can be measured, random errors associated with the temporal variability of radon can be minimized by increasing the period of measurements and number of measurements, can be modeled with seasonal correction factors. Random errors associated with the spatial variability in code. This can be minimized by increasing the number of monitoring rooms. Also can be estimated by studying the internal variability in holes. And also so-called Bergson errors. Cannot be measured, but can be modeled if this is necessary. And I would like to thank you for your attention. I'm sorry because maybe you hear some noise. My neighbor decided to start building exactly today, so to build something. So I'm really sorry if you hear this additional noise, but it is the joy of obviously live presentation.
Thank you, Sori, and thank you for your patience with the audience also to correct the presentation. At least you could see Sori's presentation.
Yeah.
I think we can.
There's something technical difficulties.
So Maria, you have some questions and that we can read and hopefully get some answers to from Sori.
Yeah, so the first comment is more a question of whether we can share the presentation. We'll look into this and get back to you, I'd say, in that one. Second question, I think, is a very, very good one because it's probably something a lot of us comes across. So this is a question about the reality of measurement in the field. So with the easy availability of the continuous digital measurement devices.
Could you please say again? What is the question?
Sorry, so with the electronic monitors being so easily available as they are,
yes.
This particular person is pointing out that they're finding customers, and this is both business owners and homeowners, are becoming obsessed with the peaks in their continuous measurement, and instead of the long-term averages. Do you have any comments on how you can,
Yes, okay. We have been studying these instruments for several years, well, including COVID, unfortunately. What we noticed that first, these instruments need calibration because some manufacturers claim that they don't need calibration. This is not right. Secondly, they can show short-term variation, day-to-day variation, or even now hourly variations of radon. And if you can see from my presentation, if you have the short-term measurements, these measurements cannot be extended to annual average radon concentration. So if you are using these instruments just to estimate the annual average, first, this should be calibrated. And secondly, they should be left, and only the long-term average radon concentration should be used. These short spikes they are real probably, but they are not significant. What we are interested is exposure from radon, isn't it?
Thank you. Now, I have a follow-on question on this then. So say here in the UK, we are obviously most of the cheaper electronic instruments, they're not calibrated. So that's one discussion I normally have with customers to say, look, you need to understand 200 on your instrument is not necessarily equivalent to the 200 action level. But also, would you have any recommendation for how long they should leave the electronic device in to get a rough idea of a sensible long-term average? Because again, there's a difference, of course, in the different instruments as to, you know, what period. Are we looking at 3 months, like with passive trackage?
Yes. If these instruments are used to replace the passive detectors, they should be left in the same way as passive detectors, undisturbed, for 3 months at least. In UK, we have seasonal correction factors that you can use, but they can be left even for a year. But it is, I would like just to stress how important it is to calibrate them, because we have devices from the same manufacturer and the difference between them is significant. So you cannot just buy over shelf and you assume that what you're seeing is the result, it's real. You have to ask for a calibration, probably manufacturer, I think. But also these devices should be calibrated the best annually in the best places.
Super. Thank you. Now we have another question that has come in, and that says, could you emphasize, well, could you do, what are your conclusion on the same uncertainties between the electronic and the trackage detectors? Do you have any sort of comparison on the uncertainties?
Yes, we had a study and we presented results in a conference a few years ago, and we at the moment are actually preparing a paper. We compare about 7 or 8 types of IRIT instruments with passive detectors for 3 months. And some of them show very good results in comparison with passive detectors. But again, they differ between themselves, so they should first be calibrated and then they should be left undisturbed if they would like to be used as the same way as passive detectors. And you also should be careful about the memory problems of some of these devices. And also the battery should be checked and ideally replaced at the beginning. And if they are working only on main, you have to make sure that obviously there's no interruption if the data cannot be saved, because there are instruments like Raman, for example. But as with everything, if you're using according to the rules and advice, it is fine. But you cannot just go from room to room, look at the screen and see, oh, I could measure, I could see what I see, because it's not working like this. These devices also need some time to adjust themselves to the radon level, so they should not be normally read before the 1 or 2 days. And
Super, thank you. Oh, we have got more questions. So facing climate change, in your opinion, seasonal correction factors, should they be reconsidered?
European seasonal correction factors or UK seasonal correction factors?
Oh, sorry, yeah. So say like, and I've wondered the same, you know, at the moment where the weather is changing so much years from year, are you taking that into consideration? Should we redo the seasonal correction factors according to the climate change?
Okay, maybe you don't know, but the research that I did include 10 years average temperature.
Okay.
So they're smoothed over 10 years. And although climate change is quite a hot topic, here in UK, we don't see much change of the climate so far. But of course, as with everything, we can review in future this correction factor. As I said, they're not done by any other year. There is a 10-year smoothing, so I believe that they're still valid.
Super, thank you. Now we have one more question come up, so I will read it up. Sorry, stop me if you need to, because it is fairly long. So it follows from the presentation that the best way to reduce the total uncertainty is to clearly define the measurement room and to have a high density of measurements in the study area. Is there any data on the density of measurements per square kilometer needed to minimize the total uncertainty to a reasonable value?
Okay, here kilometers, this means that you are talking about some representative results. In this case, you have to identify the area and take a sample that is representative, which means that it can be selected through statistical method that will ensure this representation, and then to derive your results. But you know, if there are areas with elevated radon concentration, and if you'd like just to study this area, you go to this area, and in this case, you do so-called stratified sampling, which is sampling, but in this particular area. And it depends, because kilometer means that you're covering the area. But as I said, if you take the representative sample, it does not mean that you need thousands of measurements. It could be from 30 to 100. And then this measurement will be representative for this specific area.
Super, thank you. I have just spotted a couple of questions in the chat, so I'll just see if I can catch them. So,
Okay.
So there's is the arithmetic mean the best measure to calculate the radon exposure, and is the geometric mean relevant?
Well, the radon distribution is log normal. So the best way to measure probably is geometric mean, but arithmetic mean is very popular. And with passive detectors, we are calculating the average, which is arithmetic mean. But if you'd like to plot the distribution, then you should consider geometric mean and geometric standard deviation, because radon distribution is log normal. This is debatable. Some people say that it's some other, but it is Q distribution anyway. So the best model is log normal.
Thank you. And then there's another one. Any idea how to deal with the uncertainty due to COVID-19, such as less occupation of workplaces?
Yeah. Okay, in UK, actually, we calculate the annual average radon concentrations based on occupancy and seasonal correction factors. And obviously, during COVID, this is skewed. So the measurements during COVID could not be representative for the future. But so far in UK, we have so-called hybrid working for people that can work from home or offices. So it's kind of representative maybe for this particular period. But occupancy factors could be reviewed, of course, at some point. It's occupancy factors that will be eventually different. Yes.
Yeah. Thank you. Now, I don't think we have any more questions. Yeah, I think we are at the end of both chat and Q&A. Thank you very much. Sorry.
Okay, I would like to thank you for organizing this, and also for everybody that joined. Thank you so much. Thank you.
Thank you, Thori, and thank you, Maria. And we had a lot of questions this time. It's so it's a popular topic, I would say. So sorry for the difficulties with the presentations in the beginning. I would like just to stress out that you can find us on the web, the European Radon Association, and that you have a look at the Rooms conference in Bergen in September. That's it, sorry. Thank you very much for your presentation and for your time.
Yeah, I would like to thank the radon community that we still can discuss a lot of interesting topic, and radon is far away from running out of topics.
Yeah,
thank you, everybody.
Thank you.
Okay,
And bye. And we will get back with regarding the presentation will be published online. At least the recording will be online also.
Yeah.
So, and with that, I thank you all 95 participants that have been listening, and thank you, Sori, again, and thank you, Maria, for helping out. And have a good summer, I would say.
Yeah. Have a nice holiday period. Bye-bye.
Bye-bye.
Bye-bye, everybody. Enjoy the summer.